target for today and next week is hopefully we get to finish chapter 3. We'll try. We're going to try to finish chapter 3. It's still a lot of work ahead. We still have a lot of work ahead. Okay. So first of all, I will write x cubed minus 3x squared minus 5 raised to 1/2. Okay, so then you'll write f prime of x equals 1/2 x cubed minus 3x squared minus 5 to negative 1/2 times 3x squared minus 6x. And of course, I will write 3x squared minus 6x divided by 2, the square root x cubed minus 3x squared minus 5. I would prefer to factor out the 3x into x minus 2, and you'll see why in the next chapter. X cubed minus 3x squared minus 5. Now, here's another way. If we remember the following formula forever, then we cut back on writing a lot. And here's what we are going to write. We don't have to change the square root into blah to 1/2 anymore. Now, if it's the cube root, then it's a different story, sort of. I recommend changing it into a power. If it's the 4th root, change it into a power, just not to get confused. But this is the formula that we are looking at. And of course, you can rewrite it as f prime over 2 the square root of f. So this is not a bad idea to have handy. Because it's basically the same thing with the square root of x, right? The square root of x is 1 over 2 the square root of x times x prime. It happens to be 1. It's the same idea. Same concept. Okay. So I will do the other one when Ricky... Oh, done?
Yeah.
Yes? Okay. So let's take a look at the other one. So here it is. So the same concept, identical. So we bring down 5, x to the 4th plus 3x squared minus 2 to the 4th power times 4x cubed plus 6x. And yes, I would have factored out the 2x multiplied by 5, 10x, x to the 4th plus 3x squared minus 2, and then 2x plus 3. This is completely factored, completely simplified if you want, by factoring. This is what I would have done in these two. Questions for me? Okay, so let's go back where we, yes, please, Vanessa? Yes, first form.
Yeah.
Yes.
I'm not really sure how we got the 3x squared minus 6x on that second. No, go up. That's it. Oh.
3x squared minus 6x. There's this piece.
Yeah, but how do you know that's 6x? Like, because I knew.
I bring down the power, I subtract 1 from the power. I bring down the power, multiply by 3, I get 6, and subtract 1 from the power.
Okay.
These are the only rules we have. We don't have anything else. The power rule, the quotient rule, the product rule, and the chain rule. We don't have anything else available. Okay, so back to 3.4. Other questions? You had something about homework, Ricky.
Yeah.
Yes, what was it? And then Braden. Yes.
Number 31 and number 42?
You said 31 and 45?
Yeah.
31 and 45.
And 31 is on page 189.
And 45 is
198. Yeah.
very good. That's all I needed. Okay, so let's start with 31 and see what the problem was with 31. Where is it? 31, 189, 189. 31. Find the equation of the tangent line to the given curve at the specified point. Did you find the derivative?
Wait, what?
Did you find the derivative?
The derivative?
Well, you have to find the derivative. And then just plug in for the point, for the slope. Is that clear?
Yeah.
You cannot find the slope if you don't find the derivative and plug in a number. And the number would be 1. X equals 1. So you find y prime and you plug in 1. And that will be your slope. And then you have the point 1 comma 0. And you write y minus y1 equals the slope times x minus x1. Where this is your number that you just determined from here. And this is your 1 and this is your 0. Is that good enough?
Yeah.
Because we know the quotient rule and we know how to differentiate. Is that okay?
Yeah.
Okay, let's look at 45 on 198. 45. Okay, so in 45, we have limit as theta approaches 0 from sine theta divided by theta plus tangent theta. Good. So first we plug in and we notice that we observe that what happens here is 0 over 0 indeed. And you're free to choose to differentiate top and bottom using L'Hopital's rule because the case is 0 over 0. As long as when we differentiate that we don't get 0. We're not going to get 0, right, when we differentiate that. So let's go ahead. So this is limit. Theta approaches 0. Cosine theta over 1 plus secant square theta. That's all we needed to do. And now we know that when theta approaches 0, cosine approaches 1. And if cosine approaches 1, remember secant is 1 over cosine. Then secant approaches 1. If this approaches 1, 1 plus 1, and the limit is, that's it. Now, Vanessa, just don't forget what you want to ask. So 1 second. I want to mention one thing. Some of you on the test, I remember, wrote when theta approaches 0 or x approaches 0, you got 1/2, and you said 1/2 is a horizontal asymptote. Horizontal asymptotes are only behavior at infinity. So if it happens that I determine the limit when theta is approaching 5 or 10 or 0, then I get one number that does not mean a horizontal asymptote. Only when this approaches infinity or negative infinity. That's the only way. Because the horizontal asymptotes give us the trend at infinity. That's what those give us. Not the trend somewhere when theta approaches 0. So do not confuse this with when theta approaches infinity or negative infinity. Yes, please, Vanessa.
So how do you get from theta? I know the tan is equal to secant squared.
Yes, tangent prime. So
tangent prime. How do you get the 1 though? How do you go from theta plus tangent to 1?
when I differentiate x, or when I differentiate theta, or when I differentiate any variable, the derivative is 1. Okay. Just imagine y equals x. The slope of y equals x is 1. When we differentiate tangent, we get secant squared. Is everything else okay? I think, Brendan, you had a question?
Yeah,
Yes.
it's about the test, the proof form.
Yes. This little quiz?
Yeah, the quiz.
Okay, that's okay.
Could you, what I did was,
We can talk about this at the end of the class if you like.
okay,
But, so something about factoring maybe?
I'm not sure.
So you do have to bring the power down, subtract 1 from the power, and differentiate the inner function. That's the chain rule. Okay, very good. Other questions here? Anything else? Vanessa, did you have anything else? I don't remember. Okay, perfect. So, any more questions? Any other questions from or about 3.3 or 3.4 or the previous section? I do want to talk about the exponential functions a little bit. So let's do just that now, and then we'll continue. So if you remember, yes.
Sorry, is that 3.3?
No, I'm sorry.
What is
And this is still 3.4. Still 3.4. So when we proved this with the definition, we came up with what?
It's the same.
Yes, e to the x is the only function. The derivative of e to the x is e to the x. Good. Now, what do you think if I have e to the x, but this time is raised to a function u? Here's an example. E to tangent x. This is function composition. Let's identify the inner function now. Yes, because that's the first function you have to evaluate. If you are evaluating this function, let's say for 5 radians, first you have to plug in 5 here, find tangent, and then you get a number, and then you raise e to that number. Therefore, tangent is the inner function, and e to the x is the outer function. Perfect. So if I want to differentiate this by the chain rule, can anyone guess? And can anyone guess here? E to u of x
times u of x prime.
Exactly. Absolutely. So if I want to differentiate this, I don't have room, of course. So it's e to tangent x times secant x squared, secant squared x, because that's the tangent prime. Exactly. Exactly. So that was one thing that I wanted to clarify. And I like to practice with one problem here. Let's say 38. And this is on page 205. Let's copy the problem. It's y equals, and this is e raised to k tangent the square root of x. Sometimes in this book you can really can't find simple examples. So that's one of them. Not simple. Okay, so obviously we have the outer function, we have several situations here. This is the innermost function, this is the next in line, this is the third in line, and this is the fourth. So I have x. Just imagine we are evaluating this for 2 x equals 2. Then I have to plug it in. Then I have to take the square root. Although you can say x is really not a function, it's just plain fine. Then I would say this is number 1, this is number 2, and this is number 3 if you want. Then I have to apply the square root to it, get a number. Then I have to apply tangent to it. This is a constant, we don't have to worry about it. So I have a number in here, and then I apply e to the x to that number. So when we differentiate and we get dy over dx, we have to start with the outer function, e to this, but e to a function is prime is e to that function, times. Now I have to differentiate this. This is the second level. Constant stays outside. And I have to differentiate tangent. When I differentiate tangent, what do I get? Secant squared of the square root of x. Tangent the square root of x prime is secant squared of the square root of x. But now times the inner function prime, which is 1 over 2 the square root of x, as we know from a long time ago. And I should write times x prime, but that is 1. Of course, no one can simplify this. It's not possible, but I'm going to rearrange it a little bit. So I'm going to write k e to k tangent the square root of x times secant squared the square root of x, everything divided by 2 the square root of x. Just make it more compact. You cannot do anything here. Any questions?
So is it in the numerator k times?
Yes.
E?
Yes, everything is all chain rule, all products. No addition, no subtraction, no nothing else but multiplication. Yes. Yes. Okay. Here's the next question for you. Any questions? Any questions, please? Any questions? Yes, please. Savannah, go ahead. Yes?
Yes, how do we, when I put in, the inverse, the, secant squared of 0, it wasn't 1. I don't know if I have my calculator on the wrong.
Because cosine is 1, right? So secant is 1 divided by cosine. So if you put here 0, you have to get 1. Otherwise, we'll have to sell this calculator or do something to it. Mandatory. Only because cosine is 1. Maybe you put cosine inverse or something, who knows? But secant is not cosine inverse. Okay, it's a very good question, actually. So I know I digress, but this is very important. Very good question. Thank you. Okay. So I want you to understand that cosine inverse of x is not 1 over cosine x. Okay? So this is secant x. This is secant x. So if you want to determine secant, you don't have secant in the calculator. You have to put, so for example, if you want to determine secant of 7 radians, then you will have to put 1 over cosine 7 radians. If you want to determine secant of 30 degrees, you have to be in degrees, the mode degrees, 1 over cosine 30. We do not have secant in the calculator. Now, if you want to determine the inverse function of cosine, that's a totally different story. This one is arc cosine x. It's the inverse function of cosine. So cosine is defined on 0 to pi and takes values between -1 and 1. And cosine inverse is defined on -1, 1 and will give us values between 0 and pi. So we restricted the domain of cosine in order to create this inverse function. Because as you know, cosine exists everywhere. And this will not be a one-to-one function. I can find the inverse function for a one-to-one. That function is not one-to-one. So if in this, for example, you plug in pi, then the calculator should not give you any answer in the sense that it will give you an answer, but then you can't really plug in because we had to restrict the domain. So these are two different things. Better? Excellent. Very good. I needed to say that. So thank you for your question. Okay, so here is one property of the exponential function that we normally don't emphasize it enough in pre-calculus. Here it is. If I have a raised to log base a of x, does anyone remember what this equals to? Indeed. Thank you. Yes, we do not really emphasize this. Yes, please.
Because a and log of a cancel
The power. Yes, because the exponential function and the log function are inverses of each other. It's like I'm giving you $10 and I take it back. Addition of 10 and subtraction of 10, no deal. They cancel their effect on x. The same thing here. A to power and log base a of a number, they are cancel their effect on x. So now you're going to see in a moment what I'm getting at. What about this? E raised to natural log x. What will that be? Indeed, because this base and the base of natural log are the same. So it's the same idea. Now, where am I getting with this is I would like to discuss what happens and how do we determine when the base is not, how we determine the derivative when the base is not e, just any number. For example, let's say 2 to the x prime. No, you cannot bring x down and subtract 1 from the power. That's not going to work. This is not a function raised to a power. this is a function that is exponential. So we cannot apply a rule like that. The other thing that I was going to present is what happens when we differentiate a raised to a function this time. And the last example, I'm going to just go show an example with, let's say, 2 raised to tangent x. I don't know why tangent x is on my mind today. Okay, so now how do we get to the formula of a to the x? How do we get to the formula of a to the x? So is there a way of presenting a to the x as e raised to natural log? So a to the x. Can I write e raised to natural log x? A to the x. Natural log a, everything to the x. I didn't finish, sorry. So what is this piece? E raised to natural log, forget about this for a moment. Is this a or not?
Yes.
Okay, so this is this a,
Yes.
and this is the x.
Yes.
So I replaced a using that formula by e to this formula. I just replaced a in here. That's all I did, right? So a is e to natural log a, everything raised to x. Now let's differentiate a to the x. I have to differentiate this, e to natural log a. But of course, I copy the base and multiply the exponents, right? Prime. So I copy the base, multiply the exponents, and I get this. But this we know how to differentiate. Is this okay? If you are confused, raise your hand and I'll do it again. Okay, very good. Let's do this again. Maybe it's not clear. So we know that a to log base a of x is x.
Yes.
We know that. Good. So now I want to replace this x. Allow me to use a different letter because I want to use a. So I'm going to use here b and here b. Is that okay? So b raised to log base b of x is x. But now I'm going to put a in here. So then b raised to log base b of a is a. So far, so good. Finally, I want to replace b by e. E to natural log a is a. Why do I want e? Because I know how to differentiate this one. That's why I'm going back to the same thing. So therefore, a to the x is the same thing with e raised to natural log a raised to the x. Because I replaced a by e raised to natural log a raised to power x. Now I copy the base, multiply the exponents. And obviously when I want to differentiate this, I'm going to differentiate that. Bear with me, we can go back and apply it in an example. We didn't finish. I just want to show you where this is coming from. So then how do we differentiate e raised to u? We just looked at this formula a few minutes ago. It's e raised to u times? Very good. And that's what I need to do. So e raised to u, e raised to x natural log a times the inner function prime. How much is the inner function prime? Just natural log a. Because when I differentiate this is a constant, and when I differentiate x, I get 1. But what was this? What did we denote by this? Right here. E raised to x natural log a, it's a to the x. So a to the x prime is a to the x natural log a. I will not ask you to memorize this proof. It's a tiny, tiny proof. I just want you to see where it's coming from. So if we have e to the x prime, we only have e to the x. Because if we multiply by natural log e, how much is natural log e? It's the same formula, after all. So when you have a different base than e, all you have to add is to multiply by natural log of that base. So let's come back to our list, and now you will tell me the answers. How much is a to the x prime? Excellent. How much is 2 to the x prime? That's it. How much is a to u prime? Must be a to u of x times u prime of x times of a. Very good. Awesome. Times natural log a. Finally, 2 raised to tangent prime. What will you write? 2 raised to tangent x times secant squared x times natural log. Exactly. So the formula is slightly more difficult only because we have to keep in mind that whenever the base is not e, we have to multiply by natural log of that base. Now you can remember it also all together with natural log e and say, oh, natural log e, okay, natural log e is 1 if the base is e. So I would like to practice with other problems from, like, for example, 44. This formula doesn't come up too often. Yes, please. Sure. The previous one? Yes. So let's look at 44. 44 on page 205. And then I'd like to look at applications. And then move on. Y equals 2 raised to 3, which is raised to x squared. Yeah, a little bit of a torture. You don't deserve it. You're doing very well, and I'm pleased. But let's see this problem, though. 44 on 205. Y raised to y equals 2 raised to 3. And 3 is raised to x squared. Oops. Okay. Which one is the inner function? X squared, right? X squared, that's the first thing I have to evaluate. That's how you think. I have to evaluate x squared first. I get 5. Then I raise 3 to the 5th power. That's the second level. I get 15. And then I raise 2 to the 15th power, which is the third level. Okay? So dy over dx. We start with, so here's another suggestion. Just do this, as if there is nothing in there but just a function. How do I differentiate 2 to this power? 2 to it, I'm going to copy it, times this function prime times natural log 2. I'm going to write natural log 2 times this function prime. But how do I differentiate 3 to x squared? Now forget about this. So now we have 3 to a power. So it's 3 to x squared times natural log 3, but times the inner function prime, 2x. Just remember one more time. It gets confusing. The chain rule, no addition or subtraction. Please remember that. All products, all factors. So let's do this one more time. First, I'm asked to differentiate 2 to a function. 2 to a function prime is 2 to the function times natural log 2 times the function prime. But now I have 3 to x squared to differentiate. 3 to x squared prime is 3 to x squared times natural log 3 times the inner function prime, which is 2x. Yes?
So the 2 is the outer function, and the 3 to x squared is the inner function?
Yes, and x squared is the most inner. Yes. Yes. But it's a very good question. When we differentiate, we go from the outer to the inner. When we think in terms of evaluating, we go from the inner to the outer. So the reason why I'm explaining both ways is because sometimes you may not realize how many functions you have. So always start by thinking, okay, how many functions are in there? What if I have to evaluate this for 5? What do I do first? And that's the last level I differentiate. So obviously I have to have x squared first. Then I get 15. 3 to 15, that's the second level. Going from inner to the outer. And let's say I get 25, and then 2 to the 25 is the last level. But now I go back when we differentiate. I differentiate 2 to blah, blah, and then times 3 to blah, blah, and then x squared.
How do you get natural log to the second?
Okay, just remember if I have 2 to whatever function prime, it's 2 to that. It's this prime times natural log 2. Mandatory because this is not e. This is the formula we just wrote. So e to a function prime is e to a function times the function prime times natural log. I could have inserted u prime in here and then wait for natural log, but I didn't want to forget it. So I put in natural log first. Other questions? What will you do here? Nothing. You can multiply these two and say plus 1. Don't. There is no need to do that. So I will just condense it. 2x times 2 to 3x squared times 3 to x squared times natural log 2 times natural log 3. They're all products, please remember that. No addition, no subtraction other than, or division other than product. Okay. Now I would like to look at some applications to see why we're doing this. Are you interested in a function that represents rumor? That's one example here that I see. Maybe interesting. I've never looked at it. 84. Under certain circumstances, a rumor spreads according to this equation. We're going to copy it in a moment. It's a function. P of t is the proportion of the population. I have to copy that too. Proportion of population. That knows the rumor at time t. T is time. A and k are positive constants. I have to put that in my notes. Find this limit and find the rate of spread of the rumor. Graph P for this, we can skip that for now because it's a graphing calculator. I don't want to spend time right now with the graphing calculator. So 84 on page 207. We're given a function P of t, and that is I just pushed the, I think it disconnected. I just pushed the monitor a little bit, and something happened. I can't see anything. It's dead. I don't need to see, but I need to know where I am with the, it's just the empty envelope. I don't know what I did. If I need it, as I don't know when to stop the video and continue. Okay, maybe it's coming back to life. Okay, so we have P of t, which is 1 over 1 plus, yes, it came back to life. Thank you. A e to negative kt. P of t, always take notes when you solve a word problem. Always. P of t, proportion. of population that knows a rumor. Okay, t, time. A and k, positive constants. So 2 questions. Limit as t approaches infinity from p of t. And part B, the rate, find the rate of spread of the rumor. So one more time, let's go back. We're given a function. What type of function is it? It's a combo. Yes, I would definitely say it's a combo of a rational function with exponential. Not a simple situation at all. Okay, good. So we're told that this function, it represents proportion of population. Okay? T is time. A and K are constants and they're positive. We are asked to find the limit as t approaches infinity from p of t. What are we really asked if I'm asked to find the limit as t approaches infinity? What am I asked? If that's the case, or the trend eventually at infinity. Excellent, wonderful. And then when I'm asked to find the rate of change, blah, 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 what am I asked to find? That's it, awesome, great, well done. Thank you. Good, so let's start with the limit and see what happens. So limit 1 over 1 plus a e to negative kt when t approaches infinity. So let's do this together, please. That was 5, this is 6. Okay, let's do this together. T approaches infinity. This quantity approaches infinity. This is a positive constant, I don't even care about it. So this approaches infinity. What about negative infinity? Negative infinity. What about e to negative infinity? You can say negative. E to negative infinity is? Right. Right. Let's talk about it. Let's talk about it. So e to negative, I shouldn't be writing this. This is not mathematically legit. But I'm going to write it. E to negative infinity is 1 over e to infinity. This is 1 over infinity. Where will this go? Right. So when t approaches infinity, what can you say about all this piece? Where does it go? How much is 0 times a? How much is 1 plus 0? And how much is 1 over 1? So I can write now, because of this, I can write what? Because of this and this, what will I write? Y equals 1, horizontal asymptote at infinity. I cannot even look at negative infinity. Time is not negative. Okay, so we found where this function is going. Because what does this mean? It means that eventually, so the proportion is 100%. Excellent. So that was part A. And part B. So one more time, I'm going to copy P of t, 1 over 1 plus a e to negative kt. You already know me. Simplify. No negative leading coefficient. Everything in descending order. Everything as simple as possible. Factor. What do you think I'm going to do to this? Before I differentiate. The preparation before you differentiate is so crucial. Because you can spend 3 pages on something, or you can spend 1 line.
Raise it to negative x1.
Exactly. Thank you. I know who's doing problems from the previous lectures. Excellent, Vanessa. Thank you. Of course I'm going to do that. I don't want to differentiate a quotient. I'd rather differentiate the power. So P prime of t. Can anyone dictate? Stop. First step. Can I help with that, or you're fine? Okay. We bring down the power. We subtract 1 from the power. So now we have to differentiate the inner function carefully and slowly. When I differentiate 1, what do I get?
0.
When I differentiate a constant times a function, the constant stays outside. And now I differentiate the function, which is e raised to u. This is not plain t. If it were e to t, I would have written e to t and I'm done. But this is e to something blah, not just t. So this is e to negative kt times the inner function prime, which is negative k. So one more time, we bring the negative 1 in front, we subtract 1 from the power, and we differentiate the inner function. 1 prime is 0. When I differentiate the constant times the function, the constant stays outside. Now I differentiate the function. But it's e to u that we just practiced. E to u prime is e to u times the inner function prime, which is negative k. But yes, now I have the obligation of rearranging everything as condensed as possible. I see two negatives. I'm going to say k, ak, over e to kt, 1 plus a, e to negative kt to the second power. Okay, let's see what happened again. I have a negative in front, I have an a, and I have a negative k. So they are at the top, ak. This one has a negative exponent, it goes to the bottom. This one has a negative exponent, it goes to the bottom. And this is it. We were asked to find the rate of change of rumor with respect to time. Yes, please.
Wouldn't it be negative a since the k on the end of the equation is
Yes.
negative?
So I now multiply negative k by a by negative 1. Okay, anything else for me here? Okay, so this was an example of how we apply. Yes, please. Diwa, go ahead. Anything? Where I have what? Yes. P prime of t? Yes, I bring down the power. I subtract 1 from the power. And now I have to differentiate either function. 1 prime is 0. A constant times a function prime is the constant times e to u, which we just did. E to u prime is e to u times u prime. Better? Okay. You're going to eventually get to differential equations. So let's look at one more example and then move on. So here's an example on page 206, 76. Differential equations contain derivatives. So in short, we have a function e raised to rx. This is our function. Y equals e raised to rx. It says for what values of r, so we are asked to find r, does this function satisfy the differential equation? The second derivative of y minus 4 times y prime, first derivative, plus y equals 0. We're given a function, and we're asked that the function is e raised to r times x. So like e to u, function of x. We're asked to find r, and we are given this equation. Find r so that the function complies with the given condition. This I have, this I don't, this I don't, but I will. Yes, please, Vicky, go ahead.
Isn't it y